Good afternoon, a bright sunny day as you can tell from behind me. Today we're going to start on probability. Probability is probably one of my favorite topics in mathematics actually. Probability and linear algebra, but I really do like probability. Linear algebra I need. Probability I enjoy. Anyways, we're going to break this one up into probably 2 or 3 different lectures. We'll see exactly how it goes. But so our goals for today in this particular lecture, I'll probably just do the first 2 goals here, is to understand and derive sample space and events from a statement, and then to assign simple event probabilities. And we'll just go over those 2 today in this particular lecture, and then we'll do probably 2 more lectures. One of them covers odds, and the other one will cover compound probabilities, perhaps union, intersection, and complement. We'll see how that goes. So there may be 2 or 3 more calculations here. Anyways, let's get started. I'm going to turn off my camera. There we go. Okay. So if you're interested in gambling, games of chance, the likelihood of something happen, you pay close attention to probability. Probability started, in fact, as a way to understand and improve, in other words, how to win odds in gambling, particularly cards and dice. However, as it's turned out, it's a very useful branch of mathematics with applications basically in every field. It's really important to understanding risk management, to diversification of investment portfolios, designing a healthcare system, creating plans for retirement, assessing risks versus rewards from any business decisions, and a whole bunch of other stuff. So, in probability theory, an experiment or a trial is any procedure that can be infinitely repeated and has a well-defined set of possible outcomes. So we phrase everything in terms of an experiment or a trial, even though that's in reality that's not how we think of it. In probability, that's exactly how we think of it. And then it has a set of possible outcomes, and we call these sets of possible outcomes the sample space. Now, you've actually kind of seen something like this previously in the previous section, chapter 7, but that'll be demonstrated a little bit more clearly. An experiment is said to be random if it has more than one possible outcome. So rolling one die, you can get a 1, a 2, a 3, a 4, a 5, or a 6. And you don't know what it's going to be when you roll it. So that's a random experiment. Flipping a coin, you have heads or tails. For our purposes, in this chapter, all experiments are considered random. So the sample space. Generally, we denote the sample space with the letter S. And it's the set of all possible outcomes from an experiment. So I talked about flipping a coin. Well, when you flip one coin, you can get a heads or a tails. So the sample space is heads and tails. For rolling a die, a single die, your sample space is the numbers 1, 2, 3, 4, 5, 6. That's your sample space. Generally, as I said, we denote it as S. So S. An event is denoted by the letter E, and that measures the actual outcome of the experiment. So the sample space is heads and tails. The event, I flip a coin and I get heads. So the event is heads. The event is rolling a 3. And as you can see, there's different possible events that might occur, but every possible event is inside the sample space. So you would say that E is a subset of S. And then we have a bunch of examples for a sample space and events. So if you roll a die, and I just did this, the sample space is 1, 2, 3, 4, 5, 6. If you flip a coin twice, so previously I said flip a coin once, well now we're flipping it twice. If you flip a coin twice, you can get heads, 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 tails, tails, heads, tails, tails. If you have a spinner, and your spinner is divided into three sections, and this is 1, 2, 3, your sample space is in fact 1, 2, 3, 2, 3. My spinner comes up on this right here. That means our event is 3. So an event is the outcome of the experiment. It's what we measure and what we might end up getting. Rolling a 4, the event is 4. Flipping a coin twice and getting a heads the first time and tails the second time. Now, most of the time we say that it doesn't matter the order when you say a space or a set. But you'll notice that the element in the set is HT, not H, comma T. So HT is not equal to TH. They're separate events. One is flipping a coin. The first coin is heads. The second coin is tails. The other one, the first coin is tails. The second one is heads. So they're actually different total events. You can also have a compound event. And that is when you roll a die and you get even. In that case, the event would be 2, 4, 6. Flipping a coin twice and getting at least one heads. So that would be heads, 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 tails, and tails, heads. I think you should probably start to get the idea of the sample space and the events. And a lot of what we did as far as numbering and stuff in the previous section, counting, multiplying in regards to sets, it helps us determine the size of the sample space and also the size of the event space, both of which we're going to need. Now this table indicates the sample space for rolling 2 die. What you'll notice is there's 36 entries. There's 6 entries for the result of the first die and 6 entries for the result of the second die. And it depends on how you use the table. Sometimes we're going to use the table as the total. Sometimes we're going to use the table as the first die and the second die. So there's a lot of different ways you can use this table, and it changes what the sample space is. And what I mean by that is if I were to say the sample space for rolling a 7. So I'm sorry, let me repeat that. The event of rolling a 7 in this sample space is, there's a lot of 7s. Let's not do 7. Let's do a simpler one. Let's do a 3. So that would be a 2, 1. Sorry. And this is an ordered pair, so I'm going to do it like this. And 1, 2. Another way you might, and we're doing it this way just to be clear of what we're seeing, because what you'll see, it's listed that way in here. Okay? So what is the event a 7 is rolled? Well, lucky for us, I actually did this ahead of time. Well, isn't that nice? Anyways, the sample space of the event that a sum of 7 is rolled is 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. In this case, it's just this diagonal. And that's just how this table is set up. What is the event that the sum is less than 4? So let's take a look at the table and figure it out. The sum has to be less than 4, which means it can be 3, or it can be 1, or 2. You can't have 1 with 2 die. So it's going to be basically this section here, and that's your sample space, which is 1, 1, 1, 2, and 2, 1. So that's how you determine your sample space and your event space. But the goal of this chapter is probabilities. So what is the probability? And remember, it's a random event. We don't know what the outcome is going to be ahead of time. So we run the trial or the experiment. We determine an outcome, and that tells us what our probability are. Now, over a long period of time, assuming it's random, we can calculate some of these ahead of time. So, given a sample space with n simple events, the probability, assuming that each event, well, that's what the next one is. I'm going to skip that for now. Okay. The probability of event I, one element in the sample space, is denoted by PEI. And it's subject to two conditions. The probability has to lie between 0 and 1. So probabilities are always between 0 and 1. They can be 0, they can be 1, but almost always they're between them. That's one condition. The other condition is the sum of all probabilities in the experiment is equal to 1. If the probabilities you assign meet those two conditions, they're acceptable as probabilities. That doesn't mean they're accurate or correct, but they're acceptable. Now, when we're doing, generally speaking, what we're doing in this class is we're assigning probability under the equally likely assumption, which means we're using a fair coin. We're not using weighted dice. So when we're saying we flip a coin, heads or tails, we're saying that heads is just as likely as tails. Under that case, under those circumstances, and that's not always the case, obviously, otherwise we wouldn't even say a fair coin or an unweighted dice. But when we are operating under the equally likely assumption, the probability is equal to the number of elements in E divided by the number of elements in S. And we're going to use our little tree diagram here. So we're going to use a tree diagram. And this basically just kind of lays it out. So we start. We haven't done anything. We're going to flip a coin twice. The results of the first experiment, the first time we flip the coin, we get a heads and we get a tails. We do it again. We get a heads, a tails, a heads, a tails. And that gives us our 4 elements of the sample space, HH, HT, this should be a TH, I'm sorry, TH, and TT. You count them up and you'll notice, so let's write it out. So the sample space, we know what this one is, but it's HH, HT, TH, and TT. So that's a sample space. We know that there are 4 elements in the sample space. So the simple event probability, there's one of these, there's one HH, so that means 1. The number of the elements in the event space divided by 4, the number of elements in the sample space. And assigning equally likely, they all have the same weight. They're all 1/4. So now we look at what is the probability of flipping one head. Well, let's lay out the sample space size is the same. It's 4, recall. But the event space of flipping, what is the probability of flipping a head on one flip? That's 1/4. That is, there's one likelihood of it happening out of 4 total, so 1/4. I seem to have a little bit of a error here. I'm not quite sure where my error is, so I'm just going to erase some of this right here. And I'm going to change this to what is the likelihood of flipping a head on 2 flips, okay? So now we just want, so now our event space is equal to HH, right? HT and TH. The number of events in E is equal to 3. So the probability of at least of a head in one of the flips is 3/4. I'll rewrite these notes. This is a bad section. I'm going to continue down. What is the probability of flipping a head or a tail on one flip? That probability is a head or a tail and one flip. So one flip, we have two possibilities. It can be head or tail in the sample space. So in this case, our sample space is size of sample space. So I'm sorry, for this one, it's S is equal to H, comma T, and N of H, the size of it is equal to 2, right? And head or tail, there's two possibilities in the event. So it's 2 divided by 2, which equals 1. So if you can do, it basically is all the possibilities. We're covering all the possibilities. And recall that the sum of the probabilities of all events equals 1. And flipping a head or flipping a tail is all of the probabilities. What is the event that 2 of the same were flipped on 2 flips? That event is HH and TT. And looking back at our table here, that we calculated everything, we know that the probability of this event is 1/4 plus 1/4. I guess this was actually correct. So we'll keep that the way it was. There's another way to assign event probabilities. We're doing this based upon the assumption of equally likely. So we're assigning probability under the equally likely assumption. But it's not always true. If we have experimental evidence, for example, that this assumption is not true, then we should use our experimental evidence. For example, if a coin were flipped 10,000 times, we would kind of expect that half the time it would be heads and half the time it would be tails. So we would expect 5,000 times it would be heads and 5,000 times it would be tails. But if it differed, not a little bit, but a lot, significantly from that amount, we might think that it wasn't correct, that perhaps it was not a fair coin. So let's say instead we flip a coin 10,000 times and we get 3,750 heads. You know, based upon those kind of numbers, I'm going to say that's not a fair coin. I think the probability of heads is probably significantly less. And then we just use the numbers that we have to assign the probability. So we use the 3,750 divided by 10,000, and that gives us our 0.375 for probability. For heads, the probability for tails is 1 minus that, or 6,250 divided by 10,000. Coins don't typically land. Typically, you get heads or tails. You don't get an edge when you flip a coin. That does not count. So the probability is 0.625. I'm going to stop this one right here, and we'll continue in the next lecture.